Next, we will discuss the numerical method, which is the finite difference in solving the PDE. So this is the PDE that we have, which is known as Laplace equation, and it is one of the elliptic PDE. So if we refer to the second derivative center type of numerical differentiation, so where you can see this is the formula f double prime xi. So let's say you have a x dimension here, so f double prime x, so let's say you have xi here, so the point afterward, okay, is I plus 1. The point before is known as xi minus 1. So the step size between point, okay, is h. H is the step size. So since we are using the center type, okay, so you can see that it requires the I plus 1 and I minus 1. Okay, so this is the formula that we can use. So when we apply in our case, what we want to measure is delta squared t over x squared, which is this term. It can be written in this form as well, t double prime. So to compute the t double prime at point xi, so beware that the previous formula that we formed here is one dimension. So in our case here, we have two dimensions. So you have one more direction here is y. So let us give the y here to be j. So I for x direction, j for y direction. So the point here is xi and yj. So I repeat, if we can simplify this in using other symbol, t double prime xi dot yj. For example, this is the x dimension and y axis here. So at this point, this is our yj. At this point, this is our xi. Okay, here is our xi, yj. So in simple, we can say this point to be equal to t I j. So this is represent the temperature, okay, in this 2D. So the temperature at top, okay, can be represented by this symbol, temperature, okay, since this is, the x is constant, so your xi remains, so therefore your I remains when you move up or move down, okay, but your j dimension, okay, which is here, when you move up become j plus 1, move down become j minus 1. So the point next to it, okay, you can see I plus 1 here and I minus 1, and the j remains constant. So these are the 4 points nearby to the Tij, which can be written as this symbol, Ti plus 1 j on the right, Ti minus 1 j on the left, Ti j minus 1 on the bottom. So these are the 4 points. So if you want to find the double differentiation, okay, for the t double prime, you can use these two formulas. If you want to find out the differentiation with respect to x-axis, you can use this formula, okay. So delta x is the step size in x-axis. So this is your delta x between 2 points, and delta y is the step size in y-axis. So this is the minimum distance between 2 points as well. So how about Tij? So Tij is the temperature at the center here. Right? So let's say the temperature is given at the center equal to 30. So you can replace these two numbers by 30 degrees Celsius. So how about this? Ti plus 1 and Ti minus 1. You can find it on the left and the right here. So let's say here the temperature is given 10, here is 20. Then you can substitute it to be 10. So I plus 1 to be on the right hand side. So you should have 20 here and 10 here. How about this? J plus 1 and J minus 1 term. So I is constant. So J plus 1 is here, okay, at the top, and J minus 1 is at the bottom. So let's say I give the temperature at the top is 5, at the bottom is 15. So you should have J plus 1, 5 here, okay, 15 here. So once you substitute all the information, you can compute for these two differentiation. So by substitute these two equations inside the PDE, you should be able to obtain this formula. So we assume that delta x, the step size, is equal to delta y when we use the square grid. And we found that, okay, so if you refer to this 4 term, it represents I plus 1, I minus 1 is these 2 points. This is I minus 1, this is I plus 1, okay, the temperature here, you need it, and also the temperature for these 2 points, J plus 1 is here, J minus 1 is here, right? Tij, okay, is unknown that you are looking forward. You don't know the temperature at this point. So if you arrange this, okay, this term can be substitute on the right hand side, and then you get divided by -4. Then you can find the temperature at point Ij. The most important point here is, if let's say I give you the PDE, any PDE, you should be able to use the numerical method like the one shown here, and then form the mathematical model for it. So in this case, if I want to solve the Laplace equation, it's very difficult. So I have learned a numerical method to convert it into Laplacian difference equation, which is much more easy to be solved. Next, we will discuss on how to find the temperature distribution for this 2D plate by using the numerical mathematical modeling here. The previous numerical modeling equation is written here. So let's say we are given a problem where you have 100 degrees Celsius heated on the top, 0 degrees Celsius here, 50 degrees Celsius on the right, and 75 degrees Celsius on your left. So you want to know the temperature distribution within this plate. In simple, we make 9 points here, but in fact you can make more points to have a more accurate distribution. So let's assume we start with a simple version with this 9 points. So we want to know what is the temperature distribution at this 9 point. We start with the point number 1, which is 1, 1. So what does 1, 1 mean? It means that in the x direction, so this is our x direction. So your location will be defined by ij. So the I here is 1, okay, 1, 1. And the j is different, 1, 2, 3. So your j is on the y-axis. So this is your y-axis. So this is your j, okay. So j plus 1, j plus 2, and so on. So in this case, you want to compute the temperature at 1, 1. So we need to find the nearby 4 points. So the first 2 points is here and here. So for this point is known as T0, 1. And here is a T2, 1. Which is this term and this. This is our T21 and T01. The next 2 points is these two. Okay, so this is T12 and this is T02. So which is these two terms. So this is a T12 where your j is 1, 1 plus 1 is 2, plus T1, 1 minus 1, you get 0. So with that, okay, you don't know the T11, so this one you don't know. How about T21? T21 you don't know as well. T12 you don't know as well. So these are the things that you don't know. But you know about, okay, here T01 at the corner here is given 75 degrees Celsius. In fact, all the point here is 75 degrees Celsius. So we can tell the T01 here is 75. And T10 is here. So this is a T10. So same at this point, it will be 0 degrees Celsius. So once you substitute all the details inside the equation, you should obtain the first equation. So let's continue with the second point. So let's say you want to find T21. So you need to minus 4 here. Let's follow the general equation. So the rest, you need to find the temperature at 4 nearby points here. Right, so for these 2 points, T22 and the T31, so we don't know the information, so we just write it. So T11, okay, we have computed earlier, which is here, but we assume it to be unknown as well at the moment. Lastly, 0 degrees Celsius, this one we know about that, okay, which is 0. So this should be equal to 0. And eventually, if we rearrange the equation, you should be obtain the second equation like this. If you continue to solve the T31, and for the rest, you should be obtain 9 equations. So these are the equations that you obtain. You have 9 equations here. And then you have, okay, so if you count 3, 4, 5, 6, 7, 8, 9. You have 9 unknowns to be solved. And we can use the matrix approach, okay, to find our T here. So in this course we will learn about Gaussian elimination method, but for this situation, since we have a lot of zero in this case, so it will waste a lot of space and memory for the computer in order to store this zero. So in this case, we will introduce you a new method to solve this, which is the Gauss-Seidel method. So Gauss-Seidel method is an iterative method. Okay, it needs the guess value to find the root. So in this case, you have a matrix AX equal to B, where our unknown is the temperature T here, right? So to solve it, okay, we solve for the first equation. So normally we multiply A11x1. Second term, we have this. So third one. So by doing this, we get the first equation for x1 equal to b1. So to find the x1, okay, so this whole thing can be put on the right hand side, and a1 here can be divided, right? So you should be able to obtain this equation. So you can continue with the second equation here, right? So from here you can form the h21 multiply with x1, and you continue h22 multiply this, and lastly you have so you want to find the x2 from the second equation, rearrange it, you should be able to obtain it. So same thing, okay, look at the third equation here. So try yourself to rearrange and you should be able to obtain this. So you have three equations to find the unknown x1, x2 and x3. So for the Gauss-Seidel method, our initial guess for the unknown are 0. So x1, x2, x3 is 0. So in this case, so previously we obtained the three equations here. Okay, so since x2 is 0 here, x3 as well, so we can minus it. Okay, once you get the x1 from the first equation, you substitute into the second equation. So the x1 is substitute here, and also substitute to the third equation. So x3 is unknown, so we should follow the initial guess, which is equal to 0. It can be cancelled off. Then you can compute the x2. So again, you substitute the x2 to the next equation here. So by doing this, you can compute again the x3. So with that, okay, so we say that this is the result for the first iteration. So we continue for the second iteration. So for the second iteration, the x2 and x3 can be obtained from here. Okay, we can substitute it here. Then you can compute the x1 from this equation. So after that, you substitute your x1 to the next equation. Okay, so x3 can be found from the previous iteration here. Then you can compute for the x2, and you substitute the x2 to the next equation. Then you can compute the x3. So this is the result for the second iteration. So you can keep on continue until the accuracy becomes better and better. There are other types of the Jacobi iteration to solve this problem, but at the moment we won't discuss this yet. So for the Gauss-Seidel method, when we apply to the PDE, is also called as Liebmann method. So when we heard about Liebmann method, you should know that it's just the Gauss-Seidel method used in the PDE problem. It's the same thing. So previously we success to form the equation like this. This is our Tij equation, where the I is our x dimension and our j is our y dimension. So previously we have 9 points, okay, in between. So this one is 4 points, so we have more. So this is our case. We need to find 9 temperature in this plate. So for this case, your I here, okay, and your j will be here. So you want to find the temperature distribution at 1, 1, right? Where your I is 1 and your j is 1 to the mn, right? So in this case, it will be 3, 3. When we perform the iteration, the convergence criteria is very important. So over here, it mentioned that Laplace equation is diagonally dominant. So this is what it means, okay? So this is the diagonal element. So it is dominant by most of the value. So that's why we can say it's a diagonally dominant. So for this case, we can always converge to the stable solution, okay, based on this criteria. That means we can always get a good result by solving the Laplace equation using the Gauss-Seidel method. So here we have the overrelaxation and we have the iteration stopping criteria. So the iteration stopping criteria that we use here, you can see that this is the stopping criteria. So let's say we choose 1%, okay, so if let's say the approximate percent relative error that we calculate is less than 1%, then it will stop. So the magnitude of percent relative error here okay, so A stands for the approximate, can be computed by using this formula. So here Tij new means the current temperature result, and O means the previous temperature result in the last iteration. What are the relationship between these two? So for this case, normally we choose the lambda within 1 to 2. So what happens if we choose lambda equal to 1? Okay, let's try it. So when we choose lambda equal to 1, on the right side it will be equal to lambda equal to 1 new. So 1 minus 1, you get 0, nothing left. So Tij new equal to Tij new. So means when you choose lambda is equal to 1, nothing happens. It's the same effect you do not use this equation, right? So when you do this, okay, when you choose the lambda equal to 1, and then you try to get the answer, and the answer should have a low approximate percent relative error, less than 1%, only stop, and you compute how many iterations needed. So the iteration when you choose lambda equal to 1, or you do not compute this equation at all, then you get, let's say, 100 iterations to achieve 1%. In this case, if you want to fasten or accelerate the iteration, what can you do? You change the lambda between 1 to 2. So for example, you choose it to be 1.5. Okay, lambda here 1.5, you get negative 0.5. So in this way, by doing this, you should be able to obtain less number of iterations. So in this case, lambda equal to 1.5, where for this case we say we are applying the over-relaxation method. In order to fasten the process, so 100 iterations, you're able to reduce to maybe 50 iterations to get the same accuracy.